Assalamu alaikum, sir. First of all, thank you for giving us the opportunity to present our assignment. Today, our group is presenting on the topic of disjoint set union, also known as DSU, submitted as our first assignment for the CSE Data Structure course. My name is Rafsan Alam, and my teammates are Ishrak Mujib Iftee, Reduwanul Islam, Kowser Ahmed, and Najmus Sakib Mahim, and each of us will cover their respective sections in full depth. Without any further delay, let me begin. In this presentation, we will cover the following topics. First, an introduction to disjoint set union along with its historical background. Second, the representation of disjoint set union using tree structure. Third, a detailed discussions on the find and the union operation. Fourth, the application of DSU in Kruskal's algorithm. Finally, we will conclude with the real-life uses, pros and cons, and the overall conclusion of the topic. So, what exactly is a disjoint set union? At its core, DSU is a data structure that keeps track of a collection of elements where those elements are grouped into sets that do not overlap, meaning each element belongs to exactly one set at any time. That's the disjoint part. In the next few minutes, I will walk you through why DSU exists, what it actually does, and how it evolved into the powerful tool it is today. So, why do we even need DSU? Let's think about a real problem. Imagine connection between nodes appearing one by one over time. If we want to know whether two nodes are connected, we traverse the entire graph. That's become very expensive. This kind of problem shows up everywhere. In social networks, we want to know if two people are in the same friend community. In the graph problems, we check if two nodes are already connected before adding an edge. In image processing, we group pixels that belongs to the same region. Let me show you how this actually works with a simple example here. We start with 5 separate nodes, node 1, 2, 3, 4 and 5, each alone in their own group. Then node 1 and node 2 become connected. So they share one group. Node 3 and node 4 are also connected, forming another group. Now if we ask, are node 1 and node 2 are in the same group? To answer these questions, we need to find the root of node 1. It is node 1 itself. Then we find the root of node 2. It is also node 1. Now, if we ask, are node 1 and node 4 are in the same group? The root of node 1 is node 1, but the root of node 4 is node 3. The roots are different, so no, they don't belong to the same groups. That is the core power of DSU. It handles many merges and still answers these queries fast. Now, let us understand how DSU works internally. DSU represents every group as a tree, and every tree has one special node at the top, called the root or representative. The root is the leader of the group. There are two fundamental operations in DSU. The first is find of x. Given any node x, it climbs up the tree and returns the root of that group. So, in the diagram, the find of 4 will return 3 because 3 is the root of the tree. Similarly, 6 and 7 will also return 3 as their root. The second operation is union of A and B. It merges two trees that contain different nodes. Look at the before and after on the slide. Node 1 and node 2 form one tree, and node 3 and node 4 form another tree before the union operation. After calling the union of 2 and 4, they become one single tree with a shared root 1. The key rule is simple. If two nodes share the same root, they are in the same group. If their roots are different, they are not. The single rule is the entire foundation of DSU, how it works. So, let us quickly look at how DSU evolved over time, because the history is what makes it truly impressive. Bernard A. Geller and Michael J. Fisher introduced early union find techniques in 1960s. Then Robert Turgeon formally analyzed the optimized version and showed that it runs in nearly constant time, almost as fast as it gets for any practical input. It started with the most basic idea, just store groups directly as a knife sets. Then came parent trees, one root per set. Then the find and the union operations was formalized. Then two brilliant optimizations were added. The first optimization is path compression. Normally, when we search for the root of a node, we traverse up the tree one parent at a time, which takes longer than the deeper the tree is. Path compression solves this by making every node on that path point directly to the root after the first search. So, the next time we look up any of those nodes, we reach the root in a single step instead of climbing the entire chain again. The second is union by rank or union by size. Instead of randomly attaching one tree to another, we always attach the smaller trees under the larger one, keeping the trees shallow. What started with a simple idea became a core building block used in graph algorithms, minimal spanning tree, and connectivity problems everywhere. That's my part. Now I will hand over to Iftee, who will cover the naive disjoint set union implementation. Thank you very much.
In this section, we will briefly touch upon the three parts of DSU: building disjoint sets, finding to which set an element belongs to, and connecting two sets. We will use the idea of rooted trees to build intuition for these ideas. We will start with naive DSU. A DSU is a data structure used to efficiently manage groups of connected elements. It supports two important operations, find and union, which we will discuss shortly. In this section, we will not discuss about any optimizations. We use the find operation to find which set an element belongs to, and use the union operation to join two different sets. We can represent each set as a rooted tree, where the root is the representative of that set. Let's delve into the idea of sets, more specifically disjoint sets. A disjoint set is simply a collection of non-overlapping elements. This means that an element can only belong to no more than one group at a time. For example, we consider the following three sets. Here we have 1 to 3, here we have 4, 5, here we have 6 and 7. We see that all the group members are unique. This connects to the concept of partition in discrete mathematics. In a partition divides a collection of elements into non-overlapping blocks. DSU is useful since it allows us to dynamically maintain these partitions while groups start connecting with each other. This is especially important in graph algorithms, networking problems, and connectivity queries. Now let's explore how we represent these sets using DSU. We use an array called a parent array to store the index of its parent or representative, which establishes a one-way pointer between two nodes. If a node is its own parent, we call that node the root of that set. If we trace every other element, we would eventually find a node that would point to itself, which means it is its own parent. Then that is the root. For example, here we see that the numbers 3 and 4 point to 2, 6 points to 5, and 2 and 5 point to 1, which points to itself. Thus we get a tree-like structure where 1 is the root. Now we're going to briefly touch upon two fundamental operations of DSU: finding which set and elements belong to, and joining two different sets. Let's see how we find which set and elements belongs to using find operation. To do this, we will repeatedly follow the parent of each node until we find a node which points to itself. That node is the representative of that set. Visually, it looks like the root of the tree. Like in this example, the root of this tree is 1. If you climb up the parent pointer of each node of this tree, we would eventually find the root, and the function call would return 1. Now we join two different sets together using the union operation. First, we find the roots of each tree to which the element belongs to. If both the two roots are the same, then the elements are already in the same group and we need not connect. If they are not, we update one of the root's parent pointer to the other tree's node. Like in this example, where we connect the two elements 3 and 7 by updating the parent pointer of the root of 7, which is 5, we point to the root of 3, which is 1. And thus we have a joint set that is made up of the sets of 3 and 7. Now we merge these three ideas to build an IDSU. The code has three functions: make a set, find which element a set belongs to, and join two different sets. We'll go deeper into find and union functions in the next sections. If we analyze the time complexity, making a set is very efficient. It takes constant time, but the time complexities of the find and union functions depend on the height of the trees, which can easily lead to linear time complexity. Since the trees can become unbalanced and resemble a linked list structure, we can easily have O of n time complexity. In the next part, we will discuss how we can use the optimizations to drastically reduce the time it takes to execute the find and union operations. Thank you.
Assalamu alaikum. Welcome to part 3 of our DSU series. In this session, we are going to cover the find and union operations, understand why a naive implementation can be slow, and then learn to powerful optimizations that make DSU really constant time in practice. Find operation. Let's start with the find operation. Every element in a DSU belongs to a set, and each set is represented by a root node, kind of like a team captain. The find operation answers one question: which root does this element belong to? It works by following parent pointers up the tree until it reaches a node that points to itself. That's the root. It is done here in this recursive call. Two elements are in the same set if and only if their find results are equal. Here's a quick example. Say we call find on node 9. We look at its parent, that's 7, then 7's parent is 2, then 2's parent is 1, and 1 points to itself. So we return 1. The naive complexity is big of height, meaning the taller the tree, the slower the search. Union operation. Now the union operation. Union takes two elements, finds the root of each, and if they are in different sets, connects one root to the other, merging the two sets into one. The code is simple. Find root A, find root B. If they differ, set parent of B equal to A. For example, union of 3 and 7. Find of 3 returns 1. Find of 7 returns 5. Since those roots are different, we update parent of 5 equal 1. And now both trees are merged under root 1. The actual merge is just one pointer update. The expensive part is the two find calls underneath. Why naive DSU is slow? So what's the problem? In the worst case, repeated unions can create a tree that looks like a straight line. Node 8 on top, pointing down to 7, then 6, all the way down to 1. Finding anything near the bottom means climbing through every single node. That gives us big O of worst case complexity for both find and union. This happens when we keep attaching large trees under single nodes. The height just keeps growing. This motivates our two optimizations: flatten the tree and attach smaller trees under larger ones. Path compression. The first optimization is path compression. Here's the insight. Once we have done the hard work of walking up to the root, why not rewrite every node we visited to point directly to the root? That way, future searches on those same nodes take only one step. The code change is tiny. Instead of just returning the recursive call, we assign it back. Parent of B equal to find of parent of B. Let's see the effect. Before calling find on 9, the chain is 9 to 7 to 5 to 3 to 1. After that one call, all 4 nodes 3, 5, 7 and 9 now point directly to root 1. The tree is completely flat. Every future search on any of those nodes takes just one step. This dramatically reduces the cost of repeated find operations over time. Union by size and rank. The second optimization addresses the union side, union by size or rank. The idea is simple. When merging two trees, always attach the smaller or shallower tree under the large or deeper one. This prevents the tree from growing unnecessarily tall. Union by size tracks how many nodes are in each tree. The smaller tree attaches under the larger one, and we update the tree accordingly. Union by rank tracks an estimate of tree height. The lower rank tree attaches under the higher rank root. If both ranks are equal, we pick one and increment its rank by 1. Optimized DSU and complexity. Combining both operations gives us the final fully optimized DSU. This is our fully optimized C++ code for DSU. The amortized complexity of both find and union becomes big of alpha of n, where alpha is the inverse Ackermann function. This function grows so astronomically slowly that for any realistic input size, it's effectively a constant, never exceeding 4. Make it still big of 1. Find and union are both big of alpha n, practically constant time. Together, path compression and union by size or rank make DSU one of the fastest data structures for connectivity problems in the competitive programming and real-world systems alike. Thanks for watching.
This portion of the presentation focuses on the implementation of DSU. Here we will use DSU to make a minimum spanning tree using the Kruskal's algorithm and find the connected components of a graph. We used the make, find, and union functions of DSU to implement the Kruskal's algorithm. The make function creates a distinct component in the forest, and the find function checks whether the nodes U and V are already connected or not. If they are rejected. Otherwise, using the union function, U and V are connected. This code is used to implement the Kruskal's algorithm using DSU. Here we took input of the number of nodes and edges of the graph. Then we used C++ STL, vector, and fair to take the input of the edges. We used a loop to take the input of all the edges at a time. We sorted the edges in non-decreasing order as required for the Kruskal's algorithm. Using another loop, we created n distinct components in the forest. Then we traversed the edges vector and then assigned weight u and v with their respective values. Now, using the find functions, we check whether the nodes u and v are already connected. If they are rejected. Otherwise, we used the union function to merge the two nodes. We added the weight of the edge to the total weight of the tree. We will find the minimum spanning tree of this graph using the Kruskal's algorithm. We process the edges in increasing weight order and add an edge only if it does not create a cycle. Every time we select the smallest edge and check whether the nodes are already connected or not. And we do that by using this portion of the code. So if they are connected, then we just reject the edge and move to the next one. And if they are not, then the union function is activated and the weight of the edge is added to the total weight of the tree. So here, df is the smallest edge. D and f are in different components, so they are added together. And the weight of the edge is added to the total weight of the tree. Similarly, we process the next smallest edge, and which is BC. We connect BC as they are in different components and move to the next edge. And the next smallest edge is DE, and they are also connected as the nodes are in different components. Here, the next smallest edge is EF, but the nodes E and F are already connected via the path EDF. So, this portion of the codes become true, and the union and summation operations are skipped. The next smallest edge is AF. A and F are in different components, so they are connected as no cycle is formed. And the last edge is AB. A and V connects the two remaining components. Now all 6 components are connected and the minimum spanning tree is complete. Finally, this is the tree we are left with. This is the minimum spanning tree and its weight is 20. And this is the code we used to implement it. Finding the amount of connected components is very easy using DSU. So we just loop over the edges and do union operations according to input. And we use this small code to calculate the amount of connected components. So the idea is we just check whether the current selected node is the root of the component. As the amount of roots in the graph is the amount of connected components in the graph, this gives the correct answer.
Alaikum. This is Najmus Sakib Mahim. In this section, we will discuss about applications and conclusion of DSU. So we will also describe why DSU matters beyond theory. So the learning goals of these chapters are recognizing DSU patterns in real problems, mapping objects plus relations into components, understanding where DSU is powerful, and the last is knowing the main limitation before using it. In this part, I will discuss the 4 major real-life applications of DSU, such are accounts, graphs, images, and network. And if we recall the definition of DSU, the main work of DSU is to find whether two nodes or two elements are connected to each other or not. So let's move to the next page of the slide. This play page describes the how to recognize the pattern of DSU. So the DSU pattern appears everywhere in our real life. So the objects first, there should be an object, and then there should be a relationship amongst them, and then there should be components form, and last but not the least, queries. If we want to ask a question, then we will get whether two elements are connected or not. So this part also shows that the DSU is also important for searching queries like if two networks or two elements are connected or not. So let's move to the real life uses of the DSU. First one is network connectivity and dynamic grouping. DSU answers whether two machines or people or cities are connected or not. So here new cables or friendship can be added over time. So in the general case, the network connectivity can also be described DSU real life use. Here, here we can see a figure where there are three components, and three components. One component consists of three elements. They are A, B, C, and the second component only consists of two elements, D and E, and the third component F, it's only one element. So we can see that there are three components. We can connect it using DSU, and we can also see if it is possible to find out which element is connected to which network or something. So there is also a code beside this figure, which is down there here. So what's the most interesting part of this part is DSU used in networking is the dynamic grouping. The dynamic grouping ensures that if any two nodes wanted to be connected, DSU can be the best algorithm or a way to set the connection between them. Since we have discussed the networking part, let's move to the second usage in real life of DSU. Imagine the perfect example of DSU can be as complex as image. The image regions and grid components are or can be connected when there are similarity on each cell and can be unique. So in the figure we can see that there are different components such as a purple region and amber region and green region and cyan region. These each region denotes a component of this DSU. So here we can see the code by which we can draw or create a grid using the adjacent cells which are almost have same property and they are adjacent. They can be unioned by using DSU. As we see, the grid idea perfectly overlaps with DSU. Each pixel or cell is an element. Adjacent equal cells are merged. One connected region becomes one DSU set. So here's a code by which we can find the pixel or cell which are connected. So let's move on to next real life use. So in the next real life use, we will see entity merging. So the entity merging has a perfect example of accounts merging. So how can we describe this? When there are identities which are duplicates or something, there are different places shares same attributes, then we can merge those different entities called accounts. So the pattern at which accounts can be merged are: each account starts as a separate set, a shared email or phone links to accounts, and union merges duplicate records. Groups can be collected by their representative. So in the figure we can see there are two accounts such as account number 1 and account number 2. There has a similar attribute. It is a dot mail and x dot mail, and account 2 has x dot mail, at the rate mail, b at the rate mail. So in account 1 and 2 there is a one similar email, and that's what x at the rate mail. So we can merge account 1 and account 2. So it's an example for entity merging. So since we have covered this entity merging, let's move on to next real life use of DSU. So without any further ado, let's move to advantages and disadvantages of DSU. DSU is powerful, but only for the right kind of connectivity problem. Advantages of this is very simple code compared to many graph structures. Structures can be very complex, such as different types of graphs we have seen. So the nodes can be described very difficult. And then in the next part it's said that near constant time with optimizations. So the time of optimization is almost same, nor greater nor less than that. So excellent for incremental merging problems. So it can merge some incremental problems, which is excellent for DSU. So works naturally with Kruskal and component queries. Kruskal is also usage. You can say that in real life usage of DSU. So usage is small. Its memory usage is really small. The only two part is needed: parent and size rank of size or rank of arrays. And it has also some limitations, such as does not support deleting edges easily, does not store full path information, bad for shortest path or ordered range queries, only tells component membership, not root details. Rollback or persistent versions require extra care. So let's come to conclusion. Final takeaway: DSU turns grouping into fast parent updates. A small data structure with a huge impact on graph algorithms and real life clustering tasks. 5-part recap. The first part we have discussed about disjoint sets model groups. In the second part we have discussed naive trees explanation with parent pointers. In the third part we have discussed the optimization which flattens the trees, and the fourth part Kruskal uses DSU for cycles, and we have seen its example very briefly. In the fifth part, I have discussed DSU, which solves real grouping problems, and in the beside we see a mental model of DSU where B and C after merging we can get a root, and A B C D. These nodes are merged. So this is it. This is for the real life application of the DSU. So thanks for watching. Assalamu alaikum.